Okay, we're happy to continue the second half of the morning session with the part 2 of the coaction for Feynman diagrams.
Okay, thank you very much. And thanks to the organizers for putting together this great event, making it happen. So I will continue from Claude's talk. And so the material here is based on a paper that appeared last October and also some work in progress. Okay, so just to recap the story, considering Feynman integrals, which are computed in dim reg, and the simplest ones have an expansion given in multiple polylogs. Now the coaction that Claude has shown in his talk is well known on multiple polylogs, so we try to extend that then to Feynman diagrams and the integrals that they represent. So in fact, he's shown that already for the one loop case. So here we're going to build upon that in two directions. First, to move from the coaction on multiple polylogs to the coaction on hypergeometric functions, sort of summing the series in epsilon. And we propose this coaction of the form that Claude showed and argue that these coefficients can be derived from intersection numbers.
Okay.
Now, yeah, so at the end, and I'll have some comments on how we, what we found in trying to extend this to two loop examples. So here again is a different kind of example of what we've seen. So this is another one loop integral. This is, as Claude mentioned, evaluated as a scalar integral in a particular dimensionality. So this would be in 4-2 epsilon dimensions. So we have a pure integral that we're working with the thick lines to denote massive lines. So here, skipping here, so this is then what we understand as the usual expansion in, well, here just logs and dilogs, but if you go farther in the epsilon expansion, then you get a larger range of multiple polylogs. But we also have a closed form expression for it in terms of this hypergeometric function 2f1. So now we can take, for example, as our starting point, the coaction on the multiple polylogs, and then we find we can identify that in the epsilon expansion with this diagrammatic coaction, and now we'll take it to the next level and lift it to the coaction on hypergeometric functions. So here are the examples of how you would coact on the logarithms appearing in this equation. We have then also the diagrammatic version here. So we see these uncut integrals in the first entry and the corresponding cuts and these deformation terms that we've mentioned. And now I'm coming to this. So this will be an example of a coaction on a hypergeometric function, this one here. And of course, the point we want to make is that this carries exactly the same information as the other two versions of the coaction. So here I just want to argue that Feynman diagrams, or it's been claimed that Feynman diagrams in general, when evaluated in dim reg, are represented by generalized versions of hypergeometric functions. The 2f1 is the classic Gauss hypergeometric function, but any Feynman diagrams that we know of are represented by other kinds of hypergeometric functions. And these are ones that we'll look at later at two loops. If we have one massive propagator, again, this is this is very, very loose here. There are all kinds of prefactors I'm skipping out. I'm just highlighting a form of the hypergeometric equation. And here, in fact, this kind of integral can have multiple terms, and we get an Appel F4 function. So we see the dimensional regularization parameter appears in the arguments, and the kinematic and the parameters and the kinematic variables appear in the final arguments. So let's take a close look at the classic hypergeometric function, Gauss's hypergeometric function, and it's called hypergeometric because it's a generalization of geometric series where these coefficients involve Pochhammer symbols. Now we tend to look at it from the point of view of integral representations. So here Euler had an integral representation for Gauss's hypergeometric functions given by this expression. So it's a single variable integral. We have polynomials raised to some powers, and then we have some gamma function prefactors. In this story, the gamma function prefactors will play practically no role. So let's just focus on the part that's highlighted in blue here. We call the integrand omega and the integration contour gamma. Let's just take this, and now in order to sort of liberate our integral from this specific connection to 2f1, we just give the exponents rather generic names here. So we note that we are expanding around integer values of the powers of the polynomials. Note also now we have some complex numbers multiplying epsilon. So we've got one epsilon, but by introducing these coefficients, a0, a1, a sub x, now we are effectively using different epsilons, speaking to the questions that arose after the past talk. Okay, so here again is that integral, which pertains to the 2f1 hypergeometric function. Now we break this down a little bit farther. Take the integrand, and we identify two parts of it, which we both call phi. There's capital phi and small phi. So small phi is the single value differential form. So now we take the differential part, and we also take the factors raised to integer powers. The next part is the capital phi, and this is what's left over, which is the multi-valued function. Right, so just this, and Claude highlighted this in his talk as well. And from this part, we construct what's called the twist one form, d log phi, which is this. So it is a one form. It's got some visible poles here. And this twist now is sort of gives rise to the terms twisted homology and twisted cohomology, which will define the spaces we're working in to understand how to operate with this family of integrals. So from Stokes's theorem, we can see there's an equivalence. I mean, there's an equivalent to integration by parts identities. So we recognize that we can shift the small phi, the differential form, by terms of this form, where we have a Gauss-Manin connection. So what this means is that when we're looking at integrals of this form, when we look at different values for phi, what we're looking at for phi are twisted cohomology classes. So there's also a notion of twisted homology that will play less of a role in this talk, but we consider twisted cohomology, which reflects the fact that you can integrate by parts. Sorry, it always takes me a moment to get to the next slide. Okay, so here we have our setup. Now we would like to define a coaction. On this family of integrals, we have our integrand, our contour, and from those, we would like to find a coaction of this form. Now, this is the general form of a coaction that's mathematically sensible. So the question is, what are we going to want to take for these coefficients here? And what are then these new integrands and contours that we extract from the original information? So we're just given as a starting point this integral, where omega is a cohomology class, rather related to this phi, which is a twisted cohomology class, and gamma is a homology class. So what are these twisted cohomology groups? Well, this says, I found this mathematics has been pretty well developed by, and it's well presented in a book by Aomoto and Kita. So it's been well defined systematically when we have omega of this form, where we have polynomials raised to powers, which will be integers shifted by these epsilon parts. And furthermore, where the integration contour has its boundary on the zeros of those polynomials. So once we've identified mathematically what the twisted cohomology and homology groups are, we just pick some basis of each one. And a priori, they're unrelated, but given a choice of basis, you can construct these coefficients. And that's what we will do. In our examples, where these polynomials can be combined to a suitable number of positive geometries, this can be done in a natural way. So that's a setting where we claim that this works. So positive geometries are those that have corresponding canonical differential forms. Claude already showed this, having logarithmic singularities and unit residues precisely at their boundaries. And this includes all known examples of Feynman diagrams with multiple polylogarithmic expansions. If the polynomials are mostly linear, okay, well, there are classes. If they're all linear, or if you have one quadratic polynomial and the rest are linear, or maybe a few other special cases that have been detailed in this paper, then there exists a natural choice of the basis of integration contours, and it's straightforward to construct their canonical forms. And these are called D-log forms, So now what we're going to do is, if an integration contour is a positive geometry, which is the big assumption we're making, take its canonical form, capital Omega, and what we will construct is the cohomology intersection matrix, this. So I'd like to thank Simon for having introduced some of these concepts yesterday in his talk. We have the intersection number, which has this general definition of cohomology intersection number is given by an integral where you have to compactify one of your cohomology classes, take the wedge product, evaluate the integral. That's the formal definition. For practical computations, we use formulas of the type developed by Sebastian Mizera. And so in particular for D-log forms in one variable, we have this nice simple formula where really you just have to read off the residues appearing in these functions. So once we've done that, read off the residues, then we can just invert the matrix of cohomology intersection numbers and read off these coefficients and find the coaction formula that we're looking for. Okay, so here's how it will work systematically. We're given an integral that we start with. We've got our omega, gamma, integrand, and contour. And so the first item of business is to compute the dimension of cohomology and homology. Remember, we're going to try to find these bases and then construct their intersection numbers. So in order to get a basis, we would like to know, how many elements are we looking for? What's the dimension? And this is given in general by Morse theory or an Euler characteristic computation. In the simple cases of the type we've been studying, this is just the number of solutions to the equation d log phi is 0. Okay, now we construct a basis, and we don't need to have a canonical basis. We just need to find some basis. So we just choose, say, some set of our forms that are related to the polynomials we're using, and then we just use intersection numbers to check if they're linearly independent. And if we've got the right number of them and they're linearly independent, that is, if this matrix has full rank, then we say, okay, we've identified a basis. And it's similar for the cycles, for a basis of homology. There we construct their canonical forms. So then we've moved into the space of forms again, and again use cohomology intersection numbers then to check linear independence. Now here, where the factors, the polynomials are all linear, as in the case of 2f1, there is a natural basis, which is given by so-called bounded chambers. So let's dive into this example, get back to 2f1. In 2f1, our twist was given by this part. Remember the 3 linear factors now raised to these epsilon powers. So we have d log phi. All right, so first we'd like to find the size of the basis. This equation, d log phi is equals 0, amounts to a quadratic equation in U, so that has 2 solutions. We can also see if we just plot U, plotted the real value of U, it has, we look at these polynomials, right? So they've got, these are their zeros, 0, 1, and 1 over x. And so what we mean by bounded chambers are really the bounded spaces between these boundaries. So there, this is one and this is the other one. Okay, so we choose two independent contours with boundaries at the branch points. That's easy enough. Actually, we'd say we choose to integrate from 0 to 1 in one case and from 0 to 1 over x. So this would be like the sum of this bounded chamber and this bounded chamber. Okay, so then we would like to construct their canonical forms. These are the canonical forms that have d-log singularities precisely at the boundaries. So psi 1 is the canonical form associated to gamma 1. Psi 2 is associated to gamma 2, has those d-log singularities. And so it's always possible to use these same forms as the basis of twisted cohomology. So we've started with homology, the integration contours, and now we've constructed their canonical forms. That's fine. So now we can construct the matrix of intersection numbers. Right, so we take, since we're taking the same basis that we've just constructed, we compute the intersection matrix just by reading off residues, and this is what we get. And we can invert that matrix, and we claim and have checked that produces a coaction. Now, in this case, where we have d-log forms and linear polynomials, it's not at all a coincidence that you can just read overlaps as intersections. And if you've heard us talk about this work when it was at earlier stages, that was what we were doing. We were just sort of matching. See, this gamma 1 has an overlapping singularity with a gamma 2 here. So, so when you integrate one form over the other cycle, you're going to pick up a 1 over epsilon divergence here, which is the origin of this term here. Likewise, I mean, when you integrate, say, the canonical form here over itself, it has overlaps with itself at these two endpoints, and you get this term here and this term here, the log divergences. But now we're able to at least put it on this firmer mathematical footing of intersection numbers and twisted homology. So this same construction generalizes to other families of hypergeometric functions. Here's a variation now. We're still considering 2f1. Suppose we choose the same basis of homology, gamma, these two intervals, but let's choose different forms now, because let's just minimize those overlaps that I was just showing. So these are some other d-log forms. These are not the canonical forms of gamma 1 and gamma 2. But we can take the cohomology intersection numbers with the canonical forms here. And because this only has a singularity at u equals 1 and this one at 1 over x, we immediately get a diagonal matrix. So that's easy to invert, and that's nice because now the coaction formula that we can write down is this, which I've done explicitly. And since it's diagonal, it has just two terms in it. Right, so this is one term in the coaction. This is the other one. All right, just for another example, now this is a two-dimensional integral, so we have something a bit bigger to look at. So this is a definition of the Appel F3 function, its integral representation. So here, this is given in terms of 5 polynomial factors raised to different powers. Right, so if you plot all those in the real plane, and here I've just given all the zeros, the separate zeros of the polynomials, which are the lines, different names, so we can identify them. So the dimension of homology or cohomology is the number of bounded chambers, which you can easily eyeball. The number of chambers, sort of finite regions just bounded by these lines, is 4. 1, 2, 3, 4. Now we can choose, for our basis of contours, we can choose those 4, but to make the integration a little bit simpler, we combine them into regions that are all triangular. So here, this is the original one in the definition. BCG is another triangle here. ADG is another triangle here, and CDG is another triangle here. That's another choice of basis. Now, for each of those triangles, you can construct canonical forms. given by this expression. And again, we choose a basis of D-log forms, which are not precisely these canonical forms, but a different basis, so that we sort of minimize the overlapping singularities and come directly to a nice diagonal form for the intersection matrix. And I emphasize that this is nice, but this is optional. There's nothing wrong with just picking whatever forms you happen to have, filling up the whole matrix and inverting it. But in this case, where we have a diagonal matrix, we can invert it easily and get a coaction with 4 terms, which we've checked. Okay, so finally, we've also looked at appel F4. This is rather more complicated. This is a case now where we have a nonlinear factor here. And here, in order to get a nice looking coaction, now again, this was optional, we used bases available in the literature, which involved D-log forms, and where we were able to actually recognize all these integrals appearing in the coaction in terms of integrals that we can evaluate as F4. Because, I mean, one thing which is maybe a minor issue is when you're integrating over these other contours, it's not always trivial to make a change of variables such that you can immediately rewrite it as the same type of function, in this case, F3. But I mean, it's known that that can be done. So sometimes we could, if you want, you could use other methods to derive the basis such that those integrals would be easier to evaluate. Just a few remarks here. So a version of this hypergeometric coaction was proved mathematically for 2F1 and the whole Loricella FD series, which includes 2F1. And that was, in fact, presented by Francis Brown at last year's Amplitudes conference. So strictly speaking, then the left-hand side, the original integral and the first entries are considered to be motivic objects. And the second entries, those ones with the different contours, are de Rham or single valued, which is why we take mod I pi when we check the equivalence. Another small note is if you're working with actual Feynman integrals and the hypergeometric functions they involved, they typically have some kind of degeneracies in the exponents. So in the mathematics I've been describing, the theorems rely on the fact that all those epsilons are really different epsilons. And for physical Feynman integrals, there are some relations among them which would be generically excluded by the mathematical theorems. But we found in the cases that we're interested in, we can just write down this coaction, assuming generic exponents, and then take the limits that we want for the integrals we're interested in without any trouble. And so we would check this for various functions to several orders. And the construction will generalize to any kinds of positive geometries where these canonical forms exist. Okay, so in the remaining minutes, I'd like to comment on our progress in extending the diagrammatic coaction to 2 loops, and of course with views to beyond. So to do that, let me just illustrate, this is very much work in progress. I'll illustrate it with just 2 examples, the sunset with 1 massive propagator and then the sunset with 2 massive propagators. So here with 1 mass, I did show it earlier, this is also a kind of 2F1, so this is related to the 2F1 coaction. Now we have 2 masters in the top topology, and we can take them to be the ones shown here, say number 1 and number 2. Here we've, you can sometimes square a propagator, but here we've chosen to introduce a numerator. So these are still pure in 2 minus 2 epsilon dimensions. So we have 2 master integrands, so we expect 2 independent integration contours. Right, and in principle, you can imagine a maximal cut. The maximal cut is not unique. There are 2 of them. You can also imagine cutting the massive propagator. So that's a different cut. But just as we saw all these relations among cuts at 1 loop, these relations carry over, they exist. And this is, of course, closely connected to the fact that when you have 2 master integrands, a 2-dimensional cohomology, you also have a 2-dimensional homology. So we can choose which cuts we'd like to focus on for a diagrammatic coaction. Here we've chosen the maximal cuts. So 2 particular maximal cuts. And I haven't, so okay, so we're taking residues then at each of the visible propagators, and that's not quite enough to specify the integral. Here on this slide, I'm not saying exactly what 1 is and what 2 is, although you would be able to deduce it actually if you had the expressions, because they are the contours that make this equation work for the coaction. So it turns out there is a choice of contours for which we get very much the same equation for each of the two masters, where the red dashed line represents one of the maximal cuts and the blue dashed line represents the other maximal cut. And these numbers in parentheses represent the different integrands. Now the 2-mass sunset is a little bit more involved. This involves the Appel F4 function. And here we have 3 master integrals in the top topology, and we also have the additional master integral of this double tadpole. So we find, actually it's possible to represent the diagrammatic coaction in this way, where we have, so this again is one of the masters. So now I'm just being schematic here. So there are 3 masters. I'm not saying which is which, but there are, again, we just introduced some numerators such that they're all pure. So those are identified by 1, 2, 3, those sort of superscripts. And for the cuts, we have 3 different kinds of cuts. If you see there, so there's 3 maximal cuts identified in these 3 different colors, and they naturally are paired with the integral, the type that's already appearing here, and so on. And then this one is different. This is a cut of the 2 massive propagators. Right, so we've got 4 integrals in the top topology, right? The 1, 2, and 3 in the double tadpole. And again, we've got 4 contours describing the cuts, the maximal cuts, and then this one additional one. And so to save space here, I've omitted writing the 2 other equations that are exactly like this, but with these labels permuted. 1, 2, and 3. Very similar to what we observe here in the case with 1 mass. And then just for completeness, we can write the coaction on this double tadpole master, which is, of course, follows directly from what we observed at 1 loop. So we note that here we also have some kinds of deformation terms appearing here, which, the fact that this double tadpole appears in the first entries in terms associated to different cuts. So if we wanted to go on to 3 massive propagators, then we would encounter elliptic functions. And so things get much more complicated. The coaction there on the elliptic multiple polylogs and the expansion has been developed by Brudel, Dur, Dulat, Penanti, and Tancredi, but the diagrammatic and hypergeometric counterparts remain to be discovered. Diagrams, of course, you can play with different combinations, but when you actually evaluate them, it's quite a mess to work with. And the hypergeometric counterpart is also complicated because with the work we've done so far, we really depend on being able to expand the exponents around integer values. So this is work in progress with my students, Ricardo Gonzo and Martijn Hidding. Just to finish up here, some features of the 2-loop coactions that I'd like to comment on is, again, the first entries are in our space of original master integrals. The second entries are cuts, which is consistent with this very general formula that we're working with, where in the first entry we have a basis of cohomology, in the second entry we're working with a basis of integration contours. The fact that we have a fixed size of the basis implies linear dependence among all the cuts that you can imagine. So we can choose a basis of cuts which in particular leaves no loop uncut. You've noticed we're heavily using the maximal cuts. That is one principle you can use to narrow down the basis. And that ties in with the fact that, of course, to actually carry out these integrals, we are doing it loop by loop. And so properties will be inherited from what we found at 1 loop. For example, the homology relations and figuring out what to do with infinity, which, as Simon mentioned yesterday, is quite a difficult problem. Finally, the cuts are residues which are completed with integration contours. So the endpoints are chosen then at infinity or zeros of the factors that are appearing. We do not yet have a way to understand the coefficients appearing purely from geometry as in the one loop case. Again, this comes back to the question of what the space of the homology is. So to summarize, we've been able to propose a coaction on generalized hypergeometric functions, or a class of generalized hypergeometric functions that corresponds to the coactions on multiple polylogs and Feynman diagrams where applicable. And the coefficients that appear in this coaction formula are derived from intersection numbers. This small but interesting point that Feynman integrals typically have degeneracies in the exponents, and we've been able to take the limits that allow the coaction to still be valid for the Feynman diagrams that we've considered. The hypergeometric coaction then does support all our examples of Feynman diagrammatic coaction conjecturally to all orders in epsilon. Now, in the future, to understand really the deep principles at work here, we need to understand that the principles of master integrals and cuts and residues and homology relations, those should apply at all loop orders. So we need to really further understand the geometry and how to deal with non-polylogarithmic cases. Thanks.
Thank you, Ruth. Let's have a live round of applause.
Just a small.
Are there any questions? Yes. So Matt.
Yeah, great talk. So I was curious about the multivariate case, in that when people are sort of looking at multivariate intersection numbers in the context of integration by parts, there's this very, very intricate construction where they have to sort of nest things down to the one variable case. And it seems like in your case, it's much simpler than that. You can sort of just do it all at once. Can you comment on the distinction there?
Oops.
Geometries with lots of linear factors.
Sorry, you were briefly muted, Ruth. Can you start your answer over?
Sorry, am I unmuted now?
No, yeah, you're unmuted, but.
Okay, yeah, I would say it's just because we've been looking at these relatively simple geometries, the 2f1, the appel functions, they've got mostly linear factors. So it is easy just to read off the residues one variable at a time.
I see. Thank you.
David.
So thank you, Ruth, and thank you, Claude, for beautiful talks. You remarked that the sunrise diagram with only one internal mass is hypergeometric, and that's because one can view it as a two-loop diagram in which the two massless propagators are combined with a fractional power that we've been talking about. So it fits in very well with your coaction on hypergeometric series. But from the Feynman diagram point of view, cutting, that makes no sense. I mean, you can only cut something that's raised to an integer power. So how do those two aspects of your talk interplay in that example?
So I don't think I understand what's being raised to a fractional power.
When you go back to your two-loop diagram with only one mass, you
Yes.
have a loop down there with two massless particles. We can do that exactly. It just produces 1 over p squared to the 1 plus epsilon. So it fits in perfectly. That's why it's a hypergeometric function. It fits in perfectly. So we can look at the first part of your talk, in which is a one loop diagram with a fractional power giving a hypergeometric function. But in the second part, we can't do that when it comes to cuts. So have you looked at the interplay between those two things? We can't cut a fractionally, a propagator raised to a fractional power.
No, and indeed, I suppose the cut that would correspond to that would be cutting the two massless lines then? Right, yes, no, we explicitly would not do that. Doing our cuts, I mean, it would be nice to understand that you can take the cuts and do the loop integration of these generalized cuts in any order you want. In practice, that's not feasible. So yeah, in practice, we have definite orders that we prefer, and that would not be one of them, I think, but it's an interesting puzzle then, if we could to be able to reconcile that.
I should mention that again, there is a possibility of also asking questions to Claude, or for that matter, perhaps to Ruth, about part one. Rob?
Thank you, David. I just wanted to say something which may or may not be relevant to David's question. So in my paper from, I think it was 2017 with Francesca Muriello and Mark Harley, it's called Bykov-Lee Representations of Cut Feynman Integrals. We took a stab at defining more general classes of cuts. And so for the 1/2 power, in the very simple example you mentioned, I would propose perhaps you could just do some construction where you would use analytic continuation to make a definition. So in other words, start from arbitrary integer exponents and then just make the continuation from there.
Could be. As I understand it, it's very difficult to get away from the integers.
So maybe
It didn't seem too difficult for us in our paper. Okay.
So maybe I can say something. So David, when you integrate out a bubble, you get indeed the absolute exponent. Now, you should think of it a bit as it's related to what Ruth said about degeneracies, right? It is the same relation. Well, we looked at it when you the coaction formula that we write down for the 2 of 1 is indeed only valid when all the exponents are, but mathematically defined in first place when all the exponents are generic. Now, we did check, however, that they remain true if you degenerate. And what happens is very interesting. So in principle, the cycle that you have is a twisted cycle. So it's a line with 2 like circles glued at it at the end. And when you degenerate, these twisted cycles turn into circles, which is a dual statement to x to the -1 plus epsilon, giving you 1 over epsilon, and the delta function, which tells you that you localize at x equals 0. It's a dual statement to that. And it's in this way that the two things, that the degeneration happens. So if you have the 1 plus epsilon, and you expand, or you first make epsilon go to 0, it still works out. And my guess is, okay, we did not investigate what happens now. What does it mean for cutting a propagator raised to the power 1 plus epsilon? But the mechanism should be something similar. It would be similar to having the x to -1 plus epsilon in some parameter integral, and then first taking epsilon to 0 or first expanding. There will be some degeneration of the cycle in a similar way as what I described.
Thank you.
And maybe just to add to that, it's true also, I mean, in generic one-loop integrals, you'll find even more complicated hypergeometric functions, but they will always be a bit degenerate. And whereas in the particular case of the 2F1, when you go to the sunrise with a single mass at 2 loops, you have something that is a genuine 2F1, unlike in some one-loop cases where it's degenerated in some way.
All right. I suggest we thank Ruth again.